kindly has said, my name is Ivan Arau from the University of Science. I will talk about the possible connection between the quantum Jambasa relations and the dispersion relation for the numbers of the content of my talk is, of course, motivation. After I will mention briefly the number of theory at the quantum level. Then I will introduce the quantum Jambasa equations and the conjugate pairs of quantum generators. Later I will explain what it is. After then I will talk about the dispersion relations, which are constrained by the quantum Jambasa conditions. And then after I will explain the relation between the comping of Navier-Stokes bosons and the matrices appearing, and the rank of the matrices appearing in the quantum Jambasa conditions. So as you very well know, you have an action which normally is given by kinetic terms and a potential, and you can find the minimum of such potential. The vacuum can be single or degenerate depending on the combinations of the two parameters. This is a standard expansion of the potential around the vacuum result, around the minimum, and this is the mass matrix. But in a sense, when we say that the symmetry is spontaneously broken, well, it means that the action itself is still keep the full symmetry of the large group G. But the vacuum, the ground state is not invariant under the action of the full group, only under the action of a subgroup. And then we have a Cosell space, which defines the number of broken generators of the theory. And in ordinary conditions, in the relativistic case, the number of Navier-Stokes bosons is equal to the number of broken generators, and the dispersion relation is linear. This is the usual case, and this is at the quantum level, this is the condition. This is the other parameter. Notice that, well, I put the other parameter as a second rank tensor, and this condition is equivalent because it's not a symmetry with the action of the symmetry of the broken generator. So you already know very well. And my work was inspired, of course, in previous works done by Murayama and his colleagues, Haruki Watanabe, and Thomas Brauner. But the first guys to analyze this in deep detail were Nils and many years ago, 1976. They did the analysis. After, well, what Watanabe, Murayama, and Brauner did was to improve this explanation. Well, they found perhaps more general explanation for this phenomenon. Basically, if you have a system, basically this happens usually in non-relativistic systems. If you have a set of broken generators which are canonically conjugate to each other, they represent a single degree of freedom. And in addition, not only that, the Navier-Stokes boson which appear in such a case, even if it is massless, it seems to, it has a quadratic dispersion relation and nonlinear. So before that explanation, a satisfactory explanation was not possible. But they did a remarkable job, and they found the relation between broken generators and Navier-Stokes bosons. They found that the difference is equal to 1/2 the rank of matrix rho, and they defined the matrix rho in this way. These QA and QE represent the broken generators which are forming canonically conjugate pairs. This is a vacuum expectation value. Obviously, this is a non-vanishing quantity. This is independent of the type of algebra to select, but of course you have a Lie algebra. This was my proposal. What is my proposal? Well, the condition found by Murayama and colleagues is based. Let me go back. Is based on the combinations of two conditions. This one, which is the usual formulation of the spontaneous symmetry given condition, and this one, which I call it second constraint, but it's basically from this condition, you derive that the canonically conjugate pair of broken generators represent a single degree of freedom. It's not difficult to explain. You just introduce a complete set of intermediate states here, and you will find that they represent the same degree of freedom. My proposal was to analyze the combination of these two conditions, which is the commutator, basically the other parameter elevated to second rank tensor order, and the commutator with the canonically conjugate pair of broken generators. Of course, this formula is general. This is not only for non-relativistic, this is for relativistic cases. So we should recover the relativistic conditions from here whenever it is imposed, such condition. So So before proceeding, I will explain what is the quantum jump master conditions. I will explain that if I have a matrix R acting in two different spaces, and these spaces can be the same, but not necessarily. In coordinate notation, I will write this way. A is one space, this is a basis, and this is a basis of a completely different space. Okay, this contract. Now, when I say I will have three matrices acting in two of three spaces, such that they satisfy the quantum Yang-Buster conditions. So, for example, if I have the matrix 2, 3, it means I operate in space 2 and space 3. As you can see, J contract here, K contract here. When I say 1, 3, I am operating in space 1 and space 3. As you can see, contract here. These are the indices. And 1, 2 means you operate in this 2. Now, whenever you have three matrices acting in two of three spaces, then you have to satisfy this condition. This is a consistency condition. It's called quantum Yang-Buster condition, quantum Yang-Buster equation. This is in operator notation. But when I did in graphic form is given by this equality. Basically, this is the left-hand side, and this is the right-hand side of this equation. And they should be. I wrote this. This corresponds to coordinate notation, which I will explain later for somebody. Then I propose myself to, well, maybe there will not be time, but I will, at least in one case I will explain. I have these three matrices, or the parameter, and broken generators canonically connected. So you can introduce a complete set of intermediate steps here and here. And after I sum over all the vacuums, I mean, this is a key point. I mean, if the vacuum is the generator, I have to sum over all the vacuums. Otherwise I cannot apply the quantum Yang-Buster conditions. And then I define the product of three matrices, redefining them in this way. The matrix corresponding to this becomes in this way, in coordinate notation. You can notice that N and M live in the same space. So these two indexes will be tied. L and M prime, they will be tied together. K and M prime will be tied together in the same space. P and 0 in the same space. And the same for the other parameter matrix, A and 0, B and N. So I will try not to destroy the spaces. Let's say when I apply quantum Yang-Buster equations, I will keep the lines. I will just move line over line. I will not destroy them. So the quantum Yang-Buster conditions applied to the product of these three matrices is given by this. And the right hand side, this R1 is just a sum. This is sum and this sum. Okay, the other index are free. Now, I will in my convention, in the way how I developed it, I will keep together the index. For example, this P and 0 will remain together. That's why I keep P0 here. A will be with 0 also. That's why I write 0 here. And so on. I mean, for example, B and R2. B is together with N, so that's why I wrote N. So in other words, writing in this form, the quantum Yang-Buster equations, is just moving one line over the other without destroying them. Okay? I will explain in a moment what is that. And the idea then is that in addition you have to sum over all the vacuums. And the vacuums itself correspond to internalizing the quantum Yang-Buster conditions in this form. This is what I have said just now. I will keep together some index, and they will correspond to lines. And basically, the right-hand side of the expression which I wrote correspond to this product. And I under this notation, of course, analogous notation. And then after, there is some important point here. I have to change, I mean, N and N prime correspond to two intermediate set of complete, I mean, they're corresponding principally to two different kind of particles. But at the end, I will impose the condition they are the same because they come from the broken generators canonically conjugate to each other. But in principle, I will assume that they are independent. So whenever they are, for example, N primes with K, I will keep it together at 10 minutes. Okay? And so on. So when I exchange N and N prime, in such a case, I can move N, I can replace N by N prime, but in addition, I have to remember that N prime is with L. For example, N prime never separates from L. in this case, for example, n prime was one L. Well, if I exchange n prime here and n here, I have to move L over. So that's what I'm trying to say. That's why I don't destroy these spaces. And then the second set of Yang-Bastel conditions is give this equality. Okay. And under this notation, of course, we satisfy them. And we have to be careful with the notation we use, of course. But it's consistent. I mean, we made the products, they have to contract. For example, 0 has to contract with the 0 and so on. Now, graphically, what I have found is this. When I explain, when I contract n, when I replace n by n prime, exchange, basically it's equivalent to a rotation of this figure around this point. This line remains together, B and n, always together. This is what I need. I never destroy the spaces. It means that the lines remain unchanged. K and prime L, K and prime L remain together under this exchange. And the same from the right hand side, the same logic, only is a rotation around this point. Now, what I have done in operator notation basically is this change. This equation becomes this equation, and they correspond to completely independent equation. Only when n is equal to n prime, then we can assume that two sets of equations are the same. Now, but that case is not interesting. The useful case is this, when I use the Yang-Bastel conditions in this form. Basically, I replace n here, instead of n here, I row 0. Now I don't worry about not destroying it. This is a completely different case. But it's the most useful combination for my purposes. So repeating the same arguments, this equation is equivalent to this equality. This is equal to this. Under an analogous notation as before. This matrix, for example, 0 n prime corresponds to this, which is basically this part. Okay? And analogous to the others. And of course, n prime and k belong to the same space and so on. And in graphic notation, what we have is this. This is the quantum Yang-Bastel equation for this case. Right-hand side of the equation, right-hand side of the equation, the spaces remain together. Notice that this line, in the right-hand side is just moving this line down. This line is this line. That's it. A and P. A and P. Okay? I have not done anything extraordinary. And of course, you have to refine the matrices consistently with the lines. For example, this matrix AN, it means from A to N, B0, B0. And internal index, they have to swim, they have to count. Okay, the same to the right-hand side. Now, if we exchange n by n prime in this equation, keeping the lines together without destroying the spaces, then I obtain this independent set of Yang-Bastel conditions, which is equivalent to this equality. And under this notation, which I will not explain in detail because I have repeated the same and the same. And in operator notation, when you change n by n prime, basically this becomes this. The left-hand side of the old quantum Yang-Bastel condition is the twist map of the right-hand side of the new Yang-Bastel condition after exchanging n by n prime. And vice versa, this, you can detect that this is just twist map. 2, 3, 3, 2. 1, 3, 3, 1. 1, 2, 2, 1. And the same happens to this. So, you come cross, and they are separated conditions unless n is equal to n prime. But I am interested in the case when n is equal to n prime because otherwise they don't represent the same degree of freedom. And basically, the canonically conjugate condition is given by that. I mean, say that pairs of broken generators forming canonically conjugate pairs represent the same degree of freedom. So at the end, n will be equal to n prime for my proposal. Graphically, what I have done is the left-hand side of the Yang-Bastel equation becomes like this after doing this exchange. Well, I don't destroy the line. For example, A and P. You should find A and P here. Okay? And this graph, this right-hand side will be the twist map of the left-hand side. This is left-hand side, sorry. The left-hand side, this is the twist map of the right-hand side of the new condition, of the old condition, sorry. This is the twist map of this, and vice versa. This is the twist map of the old. So, I propose then, after analyzing all the possible combinations of the products, analyze the subject, which was the initial purpose, to analyze the commutator of order parameter commuted by this. canonical pair of broken generators. Then what I found is, as far, well, when I distribute the commutators, I have to be careful because it depends which convention you use, but I keep the spaces together. I never destroy them. For example, when I commute these two operators, you can see L and N prime go together. A remains with N, and so on. I mean, this N should be tied to 0, to the vacuum, and P always tied to N. So when I exchange P and L, I have to be concerned to the complete set of intermediate state pulses. So if the two sets of previous quantum Yang-Baxter equations are the same, which happens when N is equal to N prime, then this factor is equal to this factor. So and this factor is equal to this factor. So I can factorize them, but I cannot forget that they have some well, when I assume a space-time translational invariance, which is given by this condition, these exponentials will appear here. And this expression will be going this way. But as far as N and N prime represent the same degree of freedom, these exponentials here will vanish. So this expression will become like this, simplified, and this exponential we can expand. We can expand it. It's only, well, this is an impulsive method. What the convention as particle physics is used is positive for the time, negative for the space. And then the quantum Yang-Baxter equation, after I assume over the vacuums, tell me that this factor, I can factorize this and this, and I can factorize this and this. But I have to take into account the phases. I mean, basically, this factor here is exactly this factor. This is the twist map of this, you can see, 5 EVA, 80. And the interpretation from here to here, okay, thank you. From here to here, this corresponds to the time reversed version of this. So when I join these two guys, I have to take into account the corresponding change of the phase. When I do that, they become factorized in this form. Okay? So basically, in the standard formulation, well, this becomes cosine, of course. And then we know that this term should go to 0 and this term should go to 0 as in the standard case after a spatial iteration, because these are densities. I transform these to densities operators and so on. And this expression should be time dependent, so this goes to 0. But the exponential factor goes to 0 linearly, and the cosine factor goes to 0 at the lowest order quadratically. So it means that precisely because of the assumption n is equal to n prime, I can apply the quantum Yang-Baxter equation, and as a consequence, I found that the dispersion relation is quadratic because at the lowest order, the energy goes linearly to 0, and at the lowest order, the momentum goes linearly quadratic.
So if you say that n is equal to n prime, do you mean they're the same index or that they run over the same set?
Well, in principle, they are independent, but since they represent the same degree of freedom, at the end, they will become the same.
Yeah, but you sum over n and n prime.
Yeah.
There's a double sum, and then you simply restrict the sum to the diagonal sum, or do you, what do you mean exactly? But if you say, and if you put n equals to n prime, then q apparently is diagonal in this basis, and if q is diagonal in this basis, then the commutator of q with q vanishes, so there's too much going on.
Yeah,
and if q is not diagonal in this basis, then n is not equal to n prime, and then you should not have dropped your pn minus pn prime and so on. So what exactly are you assuming?
Well, this pn and pn prime, this are equal, and this goes to 1, of course. Because, I mean, when you assume that n is equal...
Well, if n is equal to n prime, then n prime is equal to 0 also, or...?
No. 0, I keep the vacuums separated from
But why? What justifies taking n equals to n prime then?
Well, that justification comes from this condition. Let me show you. Well, from this condition, if you introduce a complete set of intermediate states, of course they will be joined by the same set.
But this says nothing about matrix elements of Q between two non-vacuum states, right? This is just
No. Well, these are vacuums.
if I insert a complete set, I just get some 0 and an n0, but there's no statement about an n prime matrix.
Well, in this case, they are the same way. In this case, we're right, but let me see. Well, in general, n is different to n prime, but Pn should be equal to Pn prime. I think. Otherwise, they represent different degrees of freedom. Basically, these broken generators, if they are conjugate to each other, they should represent the same degree of freedom. So this should go to 1. This becomes like this. But it's possible that okay, I will analyze later what you said. Well, the idea, of course, the idea, if what I did is correct, is well, you factorize, and this expands linearly, this expands quadratic, and then of course this has to go to 0. They have to go to 0, and we know they go to 0. The way is how they go to 0, and this goes linearly and this goes quadratic. About the basis and so on, well, later I will have to think about it. But if this is correct, then the relation between there is a relation between the rank of, now 0, you say that if 0 is equal to n. In reality, these conditions require as many vacuums as internal states. So, in general, I will assume that the rank of this matrix represents the number of broken generators, because the rank of this matrix is n plus n prime, if they are the same as to n. So the number of broken generators is equal in general to n plus n prime. The number of Lamb-Boston bosons will be 1/2 of the rank of this matrix whenever n is equal to n prime, plus the rank of the matrix when n is different to n prime. This 1/2 factor comes from here. And we can classify the Lamb-Boston bosons by type A, where the number is given by the rank where n is different to n prime, and by type B, when n is equal to 1/2. And then in general, we have the number of Lamb-Boston bosons is type A plus type B. And the number of broken generators is just the rank of the matrices. So it will be 2 times the type B plus the type A. And then you can find a relation between the number of broken generators and the number of Lamb-Boston bosons in this way. So I generalize the result basically in the sense that instead of using the raw matrices as fundamental objects, I take the R matrices which appear in the Jan-Bastel conditions as the fundamental objects. Well, I mean, this result should be based independent in principle, but of course I have to verify what you say. So the conclusion is there is a correspondence between the quantum Jan-Bastel equation and the Lamb-Boston theory in this way. The assumption is valid only when we have canonically conjugate pairs of broken generators. You can see that if n is different to n prime, then we can never factorize these two guys. These two guys can never be factorized. Well, these two guys can never be factorized because I cannot say the two sets of quantum Jan-Bastel equations are the same. So I record just the standard case, the relativistic case, and linear dispersion relation. And the rank of the R matrix is related to the number of Lamb-Boston bosons in this number. Well, of course, I will take a look at what you said. Thank you very much.
Other question or comment?
Did you derive the Yang-Baxter equation, or did you assume the Yang-Baxter equation?
Well, I assume.
You assumed.
Well,
what's the physical motivation for that?
Well, because when you develop, well, the Jan-Bastel equations are there already. But when I develop the commutator or the other parameter.
No, but what do you mean they're there? The Yang-Baxter equation is a special feature of an R matrix that describes some integrable system and so on. The generic R matrix does not satisfy the Yang-Baxter equation, right? Special R matrices that satisfy the Yang-Baxter equation.
Yeah, sure.
So it's not guaranteed that it's satisfied if you have some matrix. You need to, it's a very special property. For example, all n particle scattering factorizes on 2 to 2 and so on. Which is, and so I was wondering what your physical intuition is that you should hold.
Well, in reality, my physical intuition, when initially seems to have, you have the spontaneous symmetry Witten condition, and you have the condition for canonically conjugate pairs of broken generators. And usually you have to develop them separately. Then I wanted to analyze the combination of the three matrices, what happened, see what happened. When I developed the commutators, of course that's an extension because anyway the commutator of the broken generators, if you have line algebra, will give you another generator. So in principle it will just be the same spontaneous symmetric between conditions. But if you develop the full commutator, I noticed that the first term, the first line of the commutator, and the last line are just the same, just one is the inversion of the other. So I tried to analyze the special properties of these two products, and I found that whenever you satisfy the quantum Yang-Baxter equations, and you translate the n to n prime, which is at the end I say should be the same, then you obtain exactly the first line and the last line, and the second and third line are the same in the commutator. So I say, okay, you can factorize. So what happens with the phases now? So when you analyze the phases, then you realize that one is the twist mount of the other. So you have to, if my interpretation is correct, this is time reversal. Then I have to do the corresponding changes in the phases when I group them. And this is more or less the physical intuition. Of course, I have to see if this is correct, I have to incorporate to more general systems to see finally. But in fact, possibly the commutator at the end can vanish, especially when you sum over all the values. It can happen, but it happens only when, in general, when the coordinate associated to the one broken generator is the same coordinate associated to the canonically conjugate pair, which I assume different initially. So in reality, it's not the same. They have some extra differences also in the parameters associated to the matrices.
Something I agree with is not.
Yeah.
For the same NM prime, same set, we have a deformation of so-called quantum. That's a quite rich system.
Yeah.
So in something for different NM set, I think it's quite impossible to have a one bar.
For different.
For different is impossible. So because in something we have a ridiculous before quantum group.
Well, I will have to analyze your comment. Yeah, of course, we are talking about quantum groups of algebras and this kind of thing. Well, still I have not, well, I wrote a completely different paper about algebras, but it's not related to this. But in this case, yeah, you're right, I have to see what is the algebra behind this, which still I have not. This is based on partially physical intuition together with some mathematical tools are really well developed, which I just incorporate and I apply. And the idea is that I never destroy the spaces. You say that I just move line over lines. Okay?
But in the final decision, you not do second and not just at the set, but pairwise.
Yeah, well,
so you kill the.
Yeah, well, the faces are different. Each matrix has different faces. So I mean different what do you say? Parameters. And those parameters go to the explanation. And then it doesn't mean, it's not necessarily true that they vanish at all.